Hello and welcome to the EMC Live webinar, Simulation of PCB Emissions. My name is Belinda Stashukevich and I'm the editor of Interference Technology, the creator of EMC Live. EMC Live is a brand new online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Andreas Barchansky. Andreas is the EMC Market Development Manager at CST. He holds a MSc degree in physics and a PhD in numerical electromagnetics from the Technical University Darmstadt. He joined CST as an application engineer in 2007. This webinar is sponsored by CST. CST offers accurate, efficient, computational solutions for electromagnetic design and analysis. Its user-friendly 3D EM simulation software enables you to choose the most appropriate method for the design and optimization of devices operating in a wide range of frequencies. This webinar is one of many. To check out our others, visit emclive2014.com. A recording of this webinar and downloadable PDFs will be available on our website shortly. This webinar will be interactive. You will be able to ask questions, and we encourage you to participate. Take a look at your go-to webinar navigation pane. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now Andreas will begin the presentation.
Okay, thank you, Belinda. So I'd like also to welcome everybody of you to my webinar about the simulation of PCB emission. So in today's webinar, I have three topics or three parts that I would like to present. And I have chosen the webinar to be, let's say, not for the simulation expert, as CST is the only simulation company that participates in this EMC Live event. I would like to give you an introduction with a very broad view on how to use simulation for EMC. So this will be the first part. In the second part, I would like to talk about a workflow for the simulation of emission, how you can use a 3D solver and a circuit solver together to obtain a very efficient and fast workflow for the simulation of emission. And in the third part, I would like to present an example on a realistic PCB and show you how the workflow that was presented in the section before can be applied to real-life problems. So let's start right away with the introduction. And when we talk about EMC during design process, I think most of you attendees that are interested in EMC would also agree with me that EMC needs to be considered throughout the complete design process. When you start to think about EMC too late in the design process, the costs involving changes that are needed might be much higher than if you would start more early into the design process. And of course, the worst case would be things like delayed time to market because of EMC issues, and this is something that most probably the managers in your company would not tolerate. So when we talk about considering EMC throughout the design process, the simulation can play a very efficient role in doing this, because simulation has some certain properties compared to measurement that are different. And first of all is, of course, you can run simulation without the need of a prototype. Thus, you can use it very early in the design stage when no prototype is ready or not the complete design is finished, because you should start in the design process early with asking yourself quite fundamental questions. What if questions? Do I actually need a metallic enclosure, or would it be sufficient to have a plastic enclosure? Do I need a shielded cable, or can I go with an unshielded twisted pair? This type of questions can be very efficiently answered by a simulation, because you don't need the full model, but you get the answer that you need at this stage of the design process. So furthermore, what you can get from the simulations, of course, some outputs that is typically not accessible by measurements. You can get, for example, the field distribution inside the PCB. This is something you simply cannot measure in a prototype. When running simulations, you have to think about the trade-off triangle. You have to think about what are the details of the model that you need at a particular time in the design process. You need to think about the accuracy that you need at this time. So that means when you start off, you will typically use models with less detail and models which maybe do not deliver so accurate results, but they are very fast to run because you would like to, for example, check out some parametric space, how the particular case will behave in this parameter space. And there is always one let's say, rule that I give to everybody who wants to start with simulation, and this rule is very simple, and it means start simple. Start with a simple model, start with the easy model, and then increase the complexity of your model. Do not start with a model trying to put everything that is possible into it, because that's not efficient to do. Always start simple and increase the complexity. This is about the simulation, the usage of simulation during the design stage, but even if you do a lot of things right during the design stage, there might be still the need for some troubleshooting at the end or in a later stage of the design stage. Even when you have constructed the prototype, there might be something that you just didn't think of, or there might be some coupling happening inside the structure that is causing you trouble. And also at this later stage, the simulation can be quite useful because it can deliver the field distribution. It can deliver the current distribution. You can use a simulation to understand, for example, if there is some coupling inside the device that you didn't think of before. This is a way that a simulation can be used even late in the design process. And you should not see the simulation being really a competitor to the measurements. They both have their properties and they can be used complementary. So when looking at the comparison of measurement and simulation, here's a slide which is trying to give you an idea how you should treat measurement and simulation. Of course, the measurement is used in the industry for already a very long time, at least for 50 years, while the simulation, let's say in the EMC industry, is 6 or 7 years old. When we talk about antenna design, it might be 20 years. But still, people would always consider the measurement to be the gold standard. So in my complete career, I didn't hear anybody saying that his measurement doesn't match the simulation. They will all say that the simulation will not the measurement. So this is something that the simulation always needs to consider, that people will always compare it to a measurement. But there are some differences when we look at measurements and simulations that I would like to point out. So in the second line you can see when you're doing a measurement, actually your measurement devices are physical objects, and they might affect the value of the field, or they might affect the field distribution. And I will show you an example of this on the next slide. In the simulation, you can choose ideal measurement devices, infinitesimally small E-field probes, for example. Also in the simulation, it is very simple to create ideal conditions. For example, you can create an ideal 10-volt DC source, which basically does not occupy any space on your PCB, in your structure. While you cannot do this in this measurement, your source will have some physical size and will not be ideal. Maybe if you use even a kind of pulsed source, it might even bring in some noise into the board that is originating from the source. So these things are different in measurement and simulation. And last but not least, the thing about the measurement is that you do not need to know anything about the product. You basically switch on the product and then you measure it. While when you run a simulation, your simulation will only be as accurate as really the data you are providing to it. So for example, the material data or the geometrical data, you need to make sure that it is actually matching to the device that you are measuring. That sounds quite simple, but I've experienced some benchmarks, for example, where simulation measurement didn't match, and after some weeks, finally the guys came up and were telling, oh, there was another structure, there was another connection in the device that I have measured, but I thought it might be not important, while exactly the simulation showed that you needed the complete data in order to reproduce the behavior of the device. So here's a paper that was presented during the EMC 2014, the EMC Europe 2014, and it's a very simple device. The paper was presented by researchers from the University of Lille in France, And they were using a very simple DC-DC converter with a bigger loop here. So here's the load and here's a loop. And they were using a probe to measure the near field, basically in the center of the loop. And they created a very simple model in CST Microwave Studio to model the loop and also model the basically the load loop and model the near field probe. And they get a very nice agreement of the simulation and measurement right here. So for up to 10 megahertz, the measured H field agrees very well. But what happens if you remove the loop in the simulation? You can see you're getting some deviation from the measurement and the simulation result, simply because the loop was affecting the field that was created by the structure. And you can see there are 6 to 7 dB difference, basically just of the loop that is closer. So this is important. This is something you should keep in mind when comparing simulation and measurements, that your measurement equipment might affect the results. And there is one last thing that I would like to talk about in this introduction, is that when we talk about simulation, there is a different types of simulation. There is typically the functional simulation that you will do early in the design stage, where you really check, for example, if you regulate a module, if we stay with the example of the DC-DC regulator, if the regulator module is working well, and you will include the controlling algorithm. So you maybe have some current sensing at the output of the DC-DC regulator, and you want to control the current by changing, for example, the frequency or the pulse width modulation. And in such a functional simulation, you will typically treat the connections being ideal, and you will not include the surrounding environment, while you of course will include the control algorithm. When going to the EMC part, we need to do something different. We will typically not include all the regulation models on the control algorithm, because that would make the EMC simulation far too complex. But what we need to consider are the effects of the physical interconnection that are placed on your PCB, because they might be, for example, unintentional antennas. They might create radiated emission, and also the surrounding environment. So one possible way, for example, how you also could include results from this early stage design is you can use waveforms calculated by the functional simulation and reuse them for your EMC simulation. And I will show you in the example section how this can be done on the example of a DC regulator. Okay, so that's about the introduction. Let me just show you what kind of workflow you can employ for calculation of emission of PCBs. So the workflow, like I already said in the introduction, will use a 3D EM simulation to analyze the structure, and then a coupled circuit simulation, that couples to the 3D simulation in order basically to obtain the results that we are interested in. The 3D EM simulation will be run in CST Microwave Studio, which is the full wave 3D simulator offered by CST. And the circuit will be done in CST Design Studio, which is typically an integral part of the CST Studio environment. And not only there is a one-way coupling where you basically run the 3D simulation, extract the values, and move on to the circuit. So this would be a one-way coupling. What CST is also offering is a two-way coupling, where the circuit simulator has access to the results that were created by the 3D solver. And by having this, you can do many tasks very quickly, and it offers you something which I tend to call field results at the speed of a circuit simulation. And I will present you in this section how this can be performed. So when talking about simulation and simulation time, each of these time steps that we see, of course, has different requirements. A 3D EM simulation needs longer than a circuit setup. But what you should not forget is that it's not only the solver time. A solver time is something that you could put in a scientific paper and telling, now my solver was faster as compared to another one. But for you running a simulation design process, not only the solver time, but also really the time of setting up the models is quite important. And I think everybody of you will agree that engineering time, an engineer sitting in front of a computer, is typically much more expensive than actually putting a few CPUs into a modern workstation. So you need a user interface import and export functionality that allows you to quickly create models. And like I said, the time requirement for this both steps is different, and the 3D EM simulation is typically taking longer, but this is something that can happen unattended. So for example, you can run a parameter sweep, a few different models overnight, and then come back to the office in the morning and use the circuit, which works almost interactively, and calculate the type of results that you want to have. So this is why I propose this coupled workflow of using both the 3D EM simulator and the circuit, just in order to get a very quick and efficient workflow. When running the simulation with a 3D solver, there are different methods. I think most of you already heard about things like the FDTD method, of the method of moments, the finite element method, and so on and so on. There is a bunch of these methods, and each of these methods has certain advantages or disadvantages, and it strongly depends on the structure for which you use this method. And as this title of today's presentation is about the emission of PCBs, I have two methods here, the time domain based on finite integration technique, or the frequency domain based on finite element method, which have been shown that are the most efficient methods for running a 3D simulation of a modern day PCB. And both methods have quite different properties, and they complement each other very well. So when we look at the time domain method, the time domain method is broadband. So if you need looking for broadband results, it's very efficient. However, it needs to run each port sequentially. So if you have many ports that should be excited, the time domain method will take longer. On the other hand, the frequency domain method goes frequency sample by frequency sample. Thus, when you need a broadband result, this will take longer. However, adding a port is not increasing much the simulation time. The time domain method is typically more efficient for very high geometric complexities, so you can use it for even highly complex PCBs, even for multiple PCBs in one model. While on the other hand, it's, for example, not efficient for low frequencies. The frequency domain method is, on the other side, efficient for the low frequency results, while it slows down or becomes impossible for very complex geometries. But we're talking really, for example, of 2 or 3 PCBs inside the housing. So that's what I call a complex geometry. So you can see that both methods are quite complementary, and that's a very general rule of thumb, I would say, and this is what we do also in the example here. We use the time domain method for the calculation of radiated emission, and the frequency domain method for the conducted emission, so the low frequency emission. But that's a very general rule that I'm giving you here, and it always might be the case that even both methods can be applied to the same problem. And what you should not mix up here, even if it's a very simple remark, is that when I tell you that there is a time or the frequency domain method, it does not mean that the results you are obtaining are only in time or in frequency domain. Because we use these solvers to analyze the geometry, and the results we are obtaining are afterwards calculated in a circuit simulation. And when you come to the circuit simulation, there is the possibility to also run different types of analysis. And I wrote down 3 different types of analysis that are very typically used for EMC problems. The first and quite simple is the S parameter task, where you calculate the S parameters, and in terms of EMC, this is very useful. For example, if you are designing a filter, if you might design, for example, a multi-stage filter, this is something for which you would use the S parameters for. Then there is the frequency domain, or the AC, small signal analysis, which giving you results in the frequency domain, voltages and currents typically in the frequency domain. And it has the possibility to apply the so-called combined results. And this is something that I would like to explain on the next slides. And combined results is the way that the circuit simulation can access field results. So this will be explained on the next slides. And the third proposition for a circuit simulation is the transient or the nonlinear transient analysis, where you run a really time domain analysis on your circuit. You can use arbitrary time signals, and you obtain voltages and currents in the time domain at the probes or at at the ports that you have defined. So typically you would use this for the simulation of switching nonlinear elements, like for example transistors. And although this is, I think, quite well known in the community to be the way for signal integrity simulations, where you look at the transient waveforms. So now I would like to go to the combined results, or to the AC task. So what is combined results? Combined results is based on the superposition principle. So it allows you to calculate the field distribution considering an attached circuit. Basically, it allows you to see how the fields inside the structure behave when a circuit was attached. So for this, you will start with the 3D solver, and each 3D solver will calculate the field pattern, or what you can see at the bottom is the current, for each port separated by each other. So what we have here is a very simple structure of two lines and two microstrip lines. They have ports at the ends, and they have one port in the center. When the 3D solver runs each port one after the other, it's basically assuming one port to be excited and all others to be terminated. So here are examples how the current distribution will look like when this particular port is excited and all others are terminated, typically with 50 ohm. This is how the current will look like. And for example, if this port is excited, this one in the center, and the others are set to be passive, you will obtain this current distribution. So this is what the 3D solver basically saves in the background. And then we move on and we define a circuit schematic. And the circuit schematic will calculate the voltages and currents at each of the pins that connects to the 3D block. And each of the pins that connects to the 3D block is basically one port in the 3D model. Once we have calculated the voltage and currents at these pins, we can apply the superposition principle and we can calculate the resulting field. And this is very, very efficient and very, very quick. And this is what I call to having the field results at the speed of a circuit. Because for even highly complex models, it just takes a minute or two. So here's an example on the structure that we have seen on the previous slide. And I have placed the ports on the circuit in a similar way they are placed in the 3D model. And what I do is I excite port 1 with some voltage. I keep port 2 and 4. These are these two ports with a high ohmic resistor. The port 5, which is in the center, just low ohmic, and port 3 is matched. So the resulting current will flow from port 1 through port 5 and will be terminated at port 3. And this is the way that combined results work. And I will show you in the next section how we can apply this to very complex boards, even having 20 or 30 ports, and calculate the resulting field, including the attached circuit, which is, I think, very, very nice way and very nice workflow for EMC simulations. So let's come to the example. Here's a demonstrator board that was created together with a company called Festo. This is a German company for automation equipment. And we did a joint project, and the idea was to have a board which contains the same type of drivers, the same type of elements. So they are single-ended drivers and differential drivers on this board. And basically, these are two boards on the same substrate. And the top board, the top side here that you can see, will show good EMC properties, while the bottom side will show some bad properties. And this is our demonstrator board that we have used for doing measurements and also for running simulation. And this I will use as the example for the following slides. So let's start with the example about the conducted emission. For the 3D simulation inside Microwave Studio, I was using the frequency domain solver because we have many ports. As you can see down here, there are many ports. So there are 3 ports at the connector, and there is an input filter which consists of 1, 2, 3, 4, 5, 6, 9 elements. So all these ports will be later on pins on the schematic where I can add my filtering elements. So there are 9 filtering elements. Then in the light blue, that's the input voltage of 24 volts. and it arrives at the voltage regulator module from Linear Technologies, from LT, which is basically a fully integrated voltage regulator. And then there is on the output side, there is the 3.3 volt net and a load that was placed into the 3.3 volt net. So this is let's say the bad version of the board. And the first thing is that we need to think about how to model this voltage regulator module. Actually, Linear Technology is providing a tool for this, which is called LT-Spice, and they offer all their regulator modules there in this tool. And you cannot use these regulator modules in another circuit simulator. You have to stick to LT-Spice. So this is why we go the way that I was also already showing in the introduction. We run this type of simulation being a behavioral model, which really allows me to define the input voltage, the output voltage, and the operating frequency of this particular voltage regulator. And then I record the switching voltage at the output of this voltage regulator and use this for the EMC simulation in the next step. So in the next step then, in order to run the EMC simulation, I go back to CST. So I have calculated the 3D model using the frequency domain solver. And now in order to obtain the results that I'm interested in, I switch to Design Studio to the circuit simulator and run the AC analysis. Here's the port, which is basically placed between the pins, between the 24 volt and the 3.3 volt pin of the voltage regulator. And this port is now excited by the spectrum of the signal that are obtained from LT-Spice. And the filter is currently modeled very simple. We have just one capacitor, just because that makes it easier to compare to measurements. And here are some elements that are placed close to the voltage regulator, while at the bottom here, what we see are the line impedance stabilization networks that are used to measure the conducted emission. And when I run the AC small signal analysis to obtain basically the conducted emission voltage, it is very, very fast. As you can see here, this type of analysis on the circuit level just takes 3 seconds. So if I would like now to exchange some elements, if I would like to tune my filter, I can do this almost interactively. I can run parameter sweeps on my filtering effects and see when the filter behaves best. So that's one important advantage of this workflow, is that once I have analyzed the structure in 3D, I can do a lot of things on the circuit simulator, still considering the effects of the real geometry. So in this example, it took 3 seconds to run the AC task, while in order to use this combined results approach to calculate the field distribution that I will show you in the next slides, it took 3 minutes for this complex PCB. So even if you change elements and you would like to see how the field distribution is changed on your PCB, you can get this type of results only in minutes if you employ this workflow that I propose here. So let's first take a look at the comparison of the simulation and measurement results. So you can see this is the version of the board with just one input capacitor, with one just filtering capacitor. And what you can see in green is the measured values, and in blue are the simulated values. So we match very well the emission at the operating frequency of the regulator. Well, we can see here that at some frequency ranges, the agreement between simulation and measurement is maybe a little bit worse than at the operating frequency. One thing that we can also read from here is that basically the measurement accuracy is down here. You can see that the measurement equipment was not working below this 5 dB microvolt. But the advantage now having a simulation model is that it allows me to see which of the elements that are mounted on the board do actually contribute to this particular part of the spectrum. So by changing the elements, I can see how does my emission, my simulated emission spectrum end, how is it modified. And what I see, for example, here, so this is the voltage regulator, as you can see here, and this is the input capacitor of the voltage regulator, that in this frequency range from 1 to 3 megahertz, the emission will strongly depend on the parasitic values of this particular input capacitor, while over here in this frequency range, this is mostly governed by the parasitic values of the output inductor. So these are things that help me to understand and help me to find the components that I can modify in order to change the performance of the emission in a particular frequency range. And these are now the plots calculated using the combined results. Like I showed, so first the 3D solver was calculating each port standalone. As you remember, this model had approximately 17 ports. But now what we see is really the resulting field when the excitation is taking place over here. And how does the current flow on the structure? So this is at 2 kilohertz, basically our low frequency, where the current can pass through the inductor onto the 3.3 plane, flow here through the load, and come back to the source. But of course, not all the current flow in this way, and there is a lot of emission, or you can see that the current also flows through the connector. Well, when we look at the higher frequency, for example, at 200 kilohertz, which is the operating frequency, you can see a quite different distribution of the current on the board. You can see that it's no longer flowing mostly to the load, but here are some decoupling capacitors, so it flows through the inductor, through the decoupling capacitor over this reference plane back to the input capacitor, showing us that at this position the input capacitor has a very strong effect on the emission, because of course the more current flows through a capacitor, the higher the effect of this particular capacitor will be. And this, for example, a way how you could optimize your structure now by looking at the current distribution and placing components there where the current is high, because they will be mostly effective there. So that's about the conducted emission. Here's an example on the same board on another part here for the simulation of radiated emission. And here I have used the time domain solver by accelerating the time domain solver with 2 GPUs, 2 NVIDIA GPUs, which gives me a nice speed up, and running the simulation just taking 31 minutes. You can see that in this particular model there are only 3 ports. So this is why the time domain solver again is efficient, because it's broadband with a lower port count. So we have our input, or let's say that the position of the driver. We have a resistor placed in a serial fashion into the trace, and a termination at the end of the trace. So this is what has been simulated, and in order to obtain the values, or in order to get the right excitation waveform, we have used an IBIS model of the component that was driving the structure. And you can see, so this is the IBIS model driving the 3D. Here is the serial resistor, and this is the high ohmic termination resistor. And running a transient signal integrity simulation here takes 40 seconds. And then I can reuse the spectrum for the transient signal integrity simulation and run again this AC task with the combined results, because combined results can not only be applied to field monitors, I can also apply this combined results idea also to, for example, field probes. So I have placed a probe at a 3-meter distance above the PCB to record the emitted field. And what I was then doing is, I was checking how do the different data that is saved inside an IBIS model. So an IBIS model can contain typical values of the driver, but they can also contain information about fast driver mode or slow driver mode. So this is what I did, that you can see here on the right-hand side. I have run the simulation with the 3 different types of the IBIS driver, and then calculated the emission from all the 3 modes. And you can see right here that the difference from 600 megahertz to 1 gigahertz is approximately 4 to 5 dB microvolt in the emission. And you can see here that I can place on the circuit schematic, so CST Design Studio is not only just a pure circuit, it also offers functionality for the management of simulation tasks. So I could place all the different tasks as basically kind of job queue into Design Studio, and run them all in an automated fashion. This is, for example, important because what we could do now is maybe move the trace around on the 3D and rerun the 3D model, and right away also get the results from all these tasks with just one push button, which making this management of tasks and also the definition of more complex simulation projects very, very convenient. One last thing that I did with this radiated emission model is that you have seen there is one series resistor right at the output of the, right at the driver side. And depending on the series resistor, of course, the emission spectrum will be changed simply because the series resistor will affect the current that is flowing through the trace, and of course the current is the source of the emission. So when I place in a 1 ohm resistor, I get one particular emission spectrum that you can see here on the left-hand side. It's going from 30 megahertz to 1 gigahertz. And I can also record the time domain voltages at the termination, basically at the end of the signal trace. And having a 1 ohm resistor, I get a quite big ringing. So the termination is what's 1000 ohm. I have a series 1 ohm resistor, basically nothing there is matched, and this is why I get such a ringing. Now I can add I can change the value of the series resistor to, for example, 50 ohm. Will match the signal trace and will give me a very nice waveform, and will of course reduce the emission here by approximately 50 dB microvolt. And think that this is something that is run on the circuit. So this again takes only 30 to 40 seconds to obtain this type of results. We do not need to rerun the 3D simulation because we have set up in this coupled workflow. And as I already said that, reducing the current on the signal trace will reduce the radiation. We could choose a higher resistor there. So if we go up to 250 ohm, we can see here on the left-hand side that of course the emission was reduced very nicely by approximately 30 dB. So this is very favorable for the emission. But of course, having the serial resistor in the signal trace has degraded the signal integrity, and this might already be maybe a signal which is no longer acceptable. So by having set up the model in this way, you can very efficiently and very quickly find the proper trade-off between the lowest emission and the acceptable signal integrity for this particular setup. So let me summarize my presentation. I have shown in the introduction how simulation and measurement can be used as complementary tools when you keep some things in mind, like for example that in a measurement, doing your measurement equipment can affect the field distribution, and it's difficult to create an ideal simulation while on this an ideal setup, while the simulation is good in creating ideal setup, but it might not include all the effects that you had in the measurement. In the second part, I was showing you the workflow for a coupled simulation of emission from a PCB, where we use the 3D solver to analyze the structure and the circuit simulation to obtain the results we are interested in. And due to the high integration level of CSD products, the circuit simulation allows you to also calculate field values, which the workflow or with the named as a feature, which is named combine results inside the CSD Studio Suite. And in the last section, I was showing you two examples on a realistic PCB, showing how conducted and radiated emission can be simulated. So I'd like to thank you for the attention, and I hand over back to Belinda.
Thanks, Andreas. We have a few questions that have come in. Can nonlinear circuit elements be included in the simulation?
Yes. So in the transient tasks, you can, when you run a transient simulation, you can include nonlinear elements. An alternative is, so at the bottom here you can see that in a transient task you can always add switching elements. An alternative is to use the switching spectrum, understand this as a noise spectrum, and put it at the driver side like I did it here. So basically, instead of modeling the switching, I just use the spectrum as the excitation of my model. So these are two possibilities you are having.
Okay.
I hope that answers. Okay.
Can we include the effect of the housing in the simulation?
Yes, sure. Because in the 3D simulation, basically there is no limitation to the geometry. You can include the housing, you can include the environment, and so on. So this is the analysis of the structure is not limited to any particular shape. You can include all the environments. Yeah.
Okay. Which PCB formats can be imported?
So we offer a list of the most popular PCB tools. You can import from Cadence. We have a plugin for the Cadence environment. We have the possibility to import from Mentor. And what has been shown to be a very nice format for importing is the ODB++, which is a generic format which most tools can write. And if none of the formats is supported by your tools, we can also load a Gerber file. So there is always a way to get the data into Studio.
Okay. Could cables be included in the models?
Yes. So I did not talk about cables in details, but we have a tool which is called CST Cable Studio, which offers advanced functionality of modeling cables where you have a hybrid approach in including cables and also being able to calculate complex cable cross-section and also shielded cables and so on. So this was not part of this webinar, but this is possible.
Okay. Another question. Which CAD formats can be imported? For example, SolidWorks?
Yes. So we also offer a quite long list of formats. You can find them, for example, in technical specification at our webpage at www.cst.com. So we support CATIA, Pro Engineer, SolidWorks, the SAT format, IGES, and I think the typical format for exchanging data is the STEP format. So there is a long list, and typically there is always a way also to get the CAD structure into Studio. Okay.
Okay. Another question. Can the driving waveform be brought in from, it says LTS PICE? I'm sorry. It may have been
yeah, sure. I mean, you can import basically the waveforms that you would like to use for the simulation. You can load them depending, and again, if we come here to the different tasks that are possible on the circuit simulation, you can import a spectrum for usage with the AC task, or you can import a transient waveform and use this as an excitation to obtain then the results. So that's both possible.
Okay, great.
Okay.
Attendees, if you have any more questions, please send them to us and we'll pass them along to Andreas to be answered. We've received quite a few inquiries on the topic. You can email us at info@emclive2014.com with specific needs and we can direct you accordingly. Please join us next year for EMC Live 2015, which takes place April 28th to 30th, 2015. Attendees, please send us an email if you have any more questions. A recording of this webinar will be available on our website, emclive2014.com. We will also send a link to all participants shortly. Thank you for attending.
Thank you for listening.